Okay. The sepulchral voice has spoken. Okay, we're being recorded. All right. So validation. I mean, there's sort of two big issues. One is false negatives and the other is false positives. So just to dispose of false negatives, they kind of worry people a lot, including me, because you see click trains in the data that should have been classified as a porpoise or whatever, and they weren't. But there's also a vast number that aren't even in the data for animals that were facing in a different direction, you know, or were too far away. And all kind of line transects, point transects, they all have this problem. And there is a very nice solution for point transects, which is called determining the effective detection radius. So that's a circle around your logger or your person with binoculars or whatever, and it's saying it's equivalent to getting everything inside that circle. So the number you miss inside the circle is the same as the number you got outside the circle. Actually, it's pretty hard work to determine it. It was determined in the Samba project, and there've been a couple of other good efforts, but mostly we don't even determine it. We just hope it stays the same, which is a kind of assumption, but actually it seems to be generally reasonable. So I won't say any more about false negatives, except that they are there, but they're not a problem. False positives are a huge problem because they're not produced by the cetaceans. So if you have a rate of like 1 a day, and you've got 1,000 animals a day, it's like nothing. But as the number of animals goes down towards zero, gets to a point where like half your detections are false, and then the animals are extinct and all your detections are false. So you've got to be able to find them. So that's what we're focusing on today. So the classifier, the FPOD classifier does a better job than the CPOD classifier in looking at the characteristics of each click. So I'm not actually going to say a huge amount about them, because what we have to do validating FPOD data is kind of look at the context of the click, because the classifier doesn't do that terribly well, but we can do it pretty well. And the sort of starting point, the best starting point, I thought, was for us to look at what different species look like, because really you kind of need experience of what they look like, and that's where we'll start. So I've put together this file, which you've got a copy of, called validation samples, and you've got the FP1 and the FP3, and it's a composite file. I've stuck together data from all sorts of sources into one file. So now I've got to see if I can find it. Oh yeah, I've got it. Great. Okay. Fit whole time range on screen. Show from start. So you kind of always start by looking at all your species over on the left there, and the high, moderate, and low quality trains. Show from start. There it is, about 270, 80 minutes. And you can see it's got NBHF, that's porpoises. Oh, actually, it isn't. Some of this is Franciscana from Hernan Petach in Babitonga Bay. And then there's a bunch of dolphin data. Then there's some sonars. Then we've got something else. And back at the end here, we've got WUTs, weak unknown train sources. So we'll kind of work through this. And what I've got open here is 3 copies of the FP1 file showing amplitude, frequency, and clicks per second, and then 3 copies of the FP3. What I'm going to do here, actually, normally you're not tremendously interested in the low quality or the unclassified trains, but I'm just going to keep everything showing here. So show from start, show next screen. Okay, so this is showing us porpoise data. Now, one of the key things about cetaceans is that they're shining their little sonar beam around the world and sweeping it around all the time because they're interested in building up a picture of the whole world ahead of them using this kind of little spotlight. And so you get these sort of flashes when the beam crosses the hydrophone. And generally, you can see that in the amplitude profile at the bottom, but you can't really easily see it here because the porpoise sounds are quite weak. And when you can't see it like that, you can make it more visible by no, doing the wrong thing here. Instead of looking at amplitude, look at the narrowband high frequency index. So suddenly the porpoises show up because they've got a high value for this index. So this index is just a sort of composite, a number made up of like how long the click is it the right kind of frequency, is the loudest cycle in the click in the right place, and we can see that we're getting very high scores here, and we also see that there are gaps. So that's as the beam leaves the hydrophone, you get gaps. These gaps are very important because sonars from boats are omnidirectional. They're not a beam sweeping around the world. They're actually a beam pointing at the bottom, but then it's reflected off in every direction. So you get a rather continuous pattern down here. And I'm just going to use the mouse wheel to move earlier in time. So you can see that they're kind of fizzling out. And then there's just random clicks that have got high values. I'll just zoom in on some of them there. So those actually have got a clear train structure. I'll just check. I'm hoping the lines are visible to you guys. So that's probably still porpoises, but they're further away. And yeah, now they've pretty much disappeared, going backwards in time. So what we're seeing here is an encounter. So this is really nice, really useful thing. You've got not a lot going on in terms of porpoise type clicks. And then as we move forwards, we get more and more as I'm moving forwards in time. And then they're kind of loud enough to hear and get recorded and classified mostly correctly. So there's one up there. Hang on, I'll just switch off that pointer text. There's a train up there which for some reason wasn't classified as a porpoise. And then typically when I'm not sure whether it shows here. Wow, actually this is rather amazing. This, I just told you that they're not continuous. They're coming in gaps, but here it's like proving me wrong. This is an astonishingly neat landmark sequence. So they click the porpoise, or actually it's a Franciscana, is clicking faster and faster as it approaches the pod. So it is actually looking at this strange thing on the seabed. We only see this from porpoises. We don't really see it from dolphins. And in this section here, it's hardly turning its acoustic gaze away from the pod. That is a quite exceptional sequence there. And it's freaked out the classifier, which says, I don't believe this is an animal, but it clearly is actually, because it belongs to this bigger sequence. Yeah, and then typically it ends rather suddenly. So it ends rather suddenly because not much sound comes out the back of the animal. So once it's swum over the top of the pod, you don't hear it anymore. So we'll just go back into this data, and I'll just remind myself what I was going to say. So the amplitude profile is lumpy. The trains often have neat amplitude humps. So that's what we can sort of see here. These nice rounded kind of contours are typical of, I'll just put that on the, yeah, you can see it in the FP1 at the bottom. They're typical of porpoises and dolphins, except dolphins often go off the top of the scale that the very limited amplitude scale the pod has. Yeah, so we've got gaps, we've got these rounded humps, we've got the kind of encounter structure, and then we've got this thing. This is showing us the species class, but it's also showing us the number of cycles, and they're coming out mostly around 6 here. And this white dot is where the loudest cycle is in the click. So I'm hoping I can show you what this means. So that's a porpoise click recorded by an FPOD, and it's sampling at 1 million samples a second. And there aren't many points for each wave in the click. And conventional sound recorders are usually sampling at half that rate or lower. So it's kind of even more hit and miss, kind of whether you get the peak of a sound. And so the FPOD then does some upsampling, and it manages to put extra points in, and it gets a better rendering of the shape of the click. And it tells us that actually the third cycle, 1, 2, 3, was the loudest, which is clearly correct, actually. So if noise gets louder, noise is going across on the 0 line, it kind of moves up, and the click gets shorter and shorter as the lower peaks submerge. So this point can kind of move a bit, but it's still a very useful thing to see. Am I on the right? Nope. I tell you what, I'll stop that PowerPoint because it's if I can. No, I wanted. I got the right one. Yeah. Okay. So that's what this white dot is. It's reading the click from the beginning to the end. It's saying here that it was on the 4th cycle. And you can see some coherence there. It's sort of staying roughly the same through the click. So that's good as well. So we were getting like all the porpoise features we wanted here. we've got gaps. We've got a varying click rate. That's in the top graph there. It's not a flat line going through. We've seen the high narrowband high frequency index. And then I've mentioned multipath there, but we'll look at that on perhaps we can find you see a lot of multipath with with dolphin click trains, but I'll just zoom in. Yeah, I'll show it to you on dolphin click trains. So have we got all our features of porpoises? Yeah, so that's kind of a classic porpoise. Well, frequency, I should mention frequency because it's up here in this narrow frequency band that that porpoises use. And if we hit the graph button, you can see that peak there. I'll just get it to graph the frequency in the FP3 file. So it's giving us a mode at 124 kilohertz, which is very typical of porpoises. You might look at that and think, what are these lower frequency things doing? And they're basically errors, because these click trains do occasionally pull in clicks that didn't really belong in the click train. So that happens. Okay, so that's porpoises. So as we move forwards in this file, we'll get through the porpoises. And now we're coming to something else, which is initially unclassified. So it's got no species class there. It's got nice rounded profiles. It's got the gaps. Yeah, it's getting kind of louder here. We might just zoom in on this one a bit. You see quite a bit of this in click trains from both porpoises and dolphins. I find this rather satisfying. What it is actually is that as the animal propels itself with tail strokes, it makes the head go up and down a bit. You've seen this in videos of them swimming underwater. You know, because the body's so kind of streamlined, the head, the tail kind of waggles the whole body. So this is the sonar beam flashing up and down across the hydrophone at the same rate as the dolphin is beating its tail. So at this point, the classifier decided those were dolphins. It wasn't too sure here. And now it's getting into more kind of stronger dolphin detections. So again, we've got this gappy quality to the amplitude profile, which is significant because sonars generally don't have this, and neither do noise sources. The frequency, which we saw in porpoises, was just a narrow kind of band. There is now spread downwards. And if I kind of zoom in on this click train here, this is very, very characteristic of dolphins. So you can see in the frequency display in the FP1 file, these vertical bands of records at different frequencies. And this is, these are multipath clusters. So if I zoom in there, you can see it. Let's zoom in on this one here. It's actually getting 5 clicks in there. So there's one like this is the maximum. There's one high frequency one at the beginning, is up at porpoise frequencies. And these clusters are incredibly valuable, particularly for the classifier, in saying these clicks all come from the same source. They've traveled along the same pathway, which has split the click because of variations in the sound speed of the water into separate pathways. Some of the click arrived from the center of the axis of the beam, and some of it came out of like slightly off center out of the melon, but got bent back towards the hydrophone. So seeing a pattern like that on its own, you can say that's got to be a cetacean. It's got to be a directional source that, well, I shouldn't have used the word directional there because you do see this from sonars. It's a good indication that it's the same source going on here. And there's an interesting thought here, actually, that you can, with the sound trap and some other WAV file recorders, you can set them to record snippets, in which case they record the loudest click, and then they kind of go deaf for a bit to avoid recording a load of other stuff. But actually they then lose this multipath information, which is a really kind of grievous loss. So we're just kind of getting to grips with what dolphins look like here. So you can also see, compared to porpoises, you've got all these colors here because of the different frequencies. You've got variation in the click rate. This value for where the loudest cycle is tends to be near the beginning of the click. Sometimes it's position 0, sometimes it's the first cycle. But again, you're seeing kind of coherence here. So I'm just going to get, have I amplitude profile lumpy, this gap, sorry, low NBHF index, early peak out, multipath is common. Okay, so I've covered the things we needed to look at there. Okay, so we're still in dolphin territory here, and it is getting fairly continuous down here. But what if I'm just using F6, but if you look at the amplitude profile, although it is fairly continuous, you've still got this very lumpy profile because the beam is kind of shifting around on and off the hydrophone. It's astonishingly useful, that amplitude profile. You know, when you're validating a lot of them, you kind of end up whizzing through and saying, yeah, dolphin, dolphin, dolphin. Okay, and we've kind of probably run out of the, I'll just zoom out here. Yeah, so that was the dolphin section. I'm just going to zoom in there, show next screen. Okay, so now we're into a bunch of sonars and we hate them. I'm just going to go earlier here to get this feeling of an encounter with a sonar. So, so in this panel 3 here, we've got the click rate, and you can see a sort of flat line emerging there. I'll just jack that up a bit with F5. You can see these dead straight lines coming through. You can also see a pretty straight line through the frequency. So if it was a dolphin or a group of dolphins, this is never as narrow as that. If it's porpoises, it will be up there, and it would have gaps in it for the reasons we've talked about. So just so that was like where it first appeared, minute 2, minute 3, minute 4. Minute 4 is the first point at which the classifier says, right, I've got click trains here. And it's classified it as a sonar. You can see that maroon sort of color. Some of the trains it wasn't sure about, and it made them unclassified. And you can see down at the bottom the amplitudes got louder. There's 2 click rates shown here, which is a bit of a surprise. So let's zoom in just by dragging across there. Okay, and suddenly we can see what it is. This sonar alternates its interpulse interval, its interclick interval, so it zigzags up and down like that. And the click rate shown here was just derived from comparing one click with the next. So you had sort of slightly shorter and slightly longer gaps. Yeah, use Control and Z to get back to where we were. Yeah, then the boat's sort of gone past. It seems it's got quieter. It just picks it up a bit more. And here in the graph at the top, you're seeing something you see a lot with sonars. This click rate here is probably the true one, or maybe it's that one up there. This one's a half. Yeah, it's that one. This one's a half. That's a third. That's a quarter. So what's happening is there are clicks missing from the record, and the train detection is struggling to find the true rate, and sometimes it's going to kind of every alternate one and or every third, etc., etc. So errors are creeping in there, and then it's gone. The straight line of frequency's gone. The straight line of click rate's gone. So so this flat line of click rate is really valuable and is an absolute kind of giveaway for sonars. So we've got some other sonars here. This one is at 85 kilohertz. So the FPOD can run the 2 sonar filters, and here it's the sonar filter kicks in at that point in that minute. In this minute, it starts very early, and it keeps it. So it's actually knocking out the sonar selectively. We initially we were kind of saying have this on as the default setting, but if you're and that's fine if you're doing porpoises. If you're doing dolphins, the sonar filter does knock out a few dolphins, and my preference now is only to use it if you're trying to work somewhere with an awful lot of sonars to just fill your data up. But anyway, it's a very easy to recognize sonar. I'll just look in this panel 5 here. I'm trying to get the length of these clicks. So they're right up at 255 cycles. They're extremely long clicks. That in itself is a complete giveaway that it's a sonar. Show next screen. Same one, I think. This one is obviously a different sonar. It's at a higher frequency there. The number of cycles here is looking much lower, and surprisingly, sonars do come in, as seen by the FPOD, as having really very few cycles. the sonar pulse has been so kind of confused by multiple reflections that it comes out as short pulses. The amplitude tends to stay fairly flat. I mean, that isn't flat, but compared to what we saw with dolphins before, hasn't got those great big peaks. But you're not seeing the click rate showing up there, and that's because you've got all this noise here. It could be propeller noise, could be sediment transport. If you wanted to check whether that click rate is showing up here, you've got to kind of get rid of the low stuff. So let's just do a graph here. Yeah, we'll put a filter in here at 90 kilohertz, miles and filters. A click filter, we'll say the minimum will be 90 kilohertz. Refresh. So that's knocked out the lower frequency stuff, and now you can see clicks per second emerging there. We've got rid of all the red stuff down there, the lower frequency noise. So you set this filter, it does the job for you, and then what happens is you forget that you've got it set, and you can't understand anything you look at for ages thereafter. So so there's a nice button over here which will clear all the filters you might have set there, or you can clear just the click filters or the train filter. I'm just going to clear the lot. Refresh. Okay, and I'll just go back to where we were, hopefully, with Control and Z. Yeah, that's the one we were on. Okay, show next screen. And we'll just bring the clicks per second down. So that's clearly a sonar from the FP3. It's sort of going, the click rate's going through in a straight line. The amplitude profile down at the bottom there is not got the gaps. And actually this sonar is so noisy, it's kind of maxing out the system. And what's happening here is the pod is trying to get to grips with it by raising its threshold. So it's nearly got it under control and is not maxing out when actually the sonar disappears. But I'll just show you in the that looks like I've still got that filter set. This green line at the bottom is the operational threshold of the pod. There's a tiny marker there which tells us kind of where we are in this. So it's just going up. Then it goes along flat because it's saying it won't immediately start falling, but it's gone quiet, stays the same, and then it starts dropping again. Clear all. I didn't click that button properly. Yeah. Okay. So that's probably our last sonar. So what we get next is a little click train here. It's quite long. It's got 30 cycles. Well, I'll just summarize the features of sonars. Yeah. So you get an amplitude profile that's got few gaps. Where are we going? Sorry. You get the flat click rate. You can have any NBHF index. I didn't show you that, but the NBHF index can be fooled by sonars. They can look very like porpoise clicks. But the peak at, yeah, I didn't show you that. I should show you that. that tends to be all over the place in the click. So I'll just go back a bit. Need to go back a bit further. Yeah, so we can see it in this fifth panel here. The little white dot telling you where the loudest cycle is kind of all over the place here. It can't actually go above position 15, even if it was above it. The software is so short of space, the file structure, that it can't accommodate that. So that's very distinctive of sonar. That, and it's because they're not, it's almost like a continuous stream of sound that's lots of overlaid pathways, and it's quite a muddle. Okay, so those were the features of sonars, and then we get back to this thing, which is long. I'm just bringing the number of cycles down. So this is actually Mach 255 cycles long. And it's a little group of pulses. So here's the first one. This one's got 8 pulses in it. They've got a lot of multipath. You can see that. Yeah. And this is probably a fish tag. So this is a fish swimming along with a little acoustic transmitter that somebody has fixed to the fish, or it may even be within the tissues of the fish. And it's conveying its information to a receiver, if there is one. I mean, in this case, the pod has received it by the gaps between these pulses. And Dave Clark and Chris Lowe in Swansea University have shown that they can pull out fish tag numbers from CPOD data, and they've been able to identify fish way up the west coast of Britain, or in Liverpool area, that would tag down on the south coast. So fish tags, yeah, they show up in the data sometimes. Okay, so now what I've got for you is some noise clicks. Actually, sorry, I'll just remind myself that I have. Oh, short groups, yeah, of long 70 kilohertz clicks. They are typically around 70 kilohertz. Those fish tags. That was the yellow color we saw. We're now on noise trains. So noise trains are not real trains. They're kind of assemblages of clicks that resemble one another, but didn't come from one source. They're like with different shrimps, different bubbles bursting, or sand grains hitting one another, whatever. These used to be the big problem about train detection, because there are vast numbers of possible noise trains, chance trains, I think of them as. And I really struggle to find some for you. They're nearly always classified as low quality and unclassified, as this one is. Just find out how many cycles it is. Yeah, it's a few cycles. So clicks per second is kind of rather low for a cetacean, but perfectly reasonable. Position of the peak is of the wave is all over the place. The amplitude profile is ragged. There aren't these round humps. There's no coherent multipath. So by coherent, I kind of mean that it's similar from click to click. It's never exactly the same, but it's similar. These have got, they are coming in clusters for some reason, but there's very little resemblance between these clusters. And when you look at the amplitude profile display of the FP1, you just see kind of stuff going along in a rather random kind of fashion. And that is noise. It could be shrimps, it could be bubbles bursting. And in your normal criteria, which would be high and moderate quality and a species, you wouldn't even see them. I've probably gone a bit too far in suppressing these things and lost some kind of good data. But that's always the dilemma with classifiers. And when I was developing the KNOF classifier, at one stage I had a sticker saying "Don't be greedy" on the top of the computer, because you kind of want to get all the detections, but you really don't want to get this stuff, because when you go somewhere really difficult, you find suddenly you're getting these things coming through. Okay, so now we're looking at something which claims to be porpoises, probably is porpoises, and the reason I've put it in is there's a train here, which actually they're kind of reasonably uniform in length, but when we see where they come from, there's nothing there. There's a little burst of sediment transport noise, and this actually, despite the uniformity there, it had an amplitude profile that was a bit ragged. The click rate, it could just be a cetacean, but it's a bit all over the place. The point I wanted to make here is that when the classifier has found good data, which it's got there, porpoises, it kind of lowers its guard a bit and pulls in other stuff and that was like not too far off being a cetacean, but it didn't it called it low quality and unclassified. So that's feedback bias on the classifier. If you're technically minded, the feedback from the classifier is actually increasing the false positive rate within that minute. Okay, show next screen. So this kind of might look like, well, it doesn't really. So this is something a bit difficult, because when we look at it, we've got this minute, and it's got this weak train down here. It's got a sort of sloping frequency profile there, and the number of clicks per second is off the top of the scale there. So I'm going to pull that down. It's like 200 or so clicks per second. And I'll zoom in on it. So this is kind of something, is it a dolphin? So this actually is a weak unknown train source, and I'm going to show you a few of these. The characteristics I have is this amplitude profile down here is rather flat through this train. There's a frequency sort of drift going on through it, which would be a bit odd in a dolphin click train. and the clicks per second has basically got a very smooth downward profile. So those were all features of a weak unknown train source. And the other kind of key feature is they're often isolated. So this is like the only thing in that minute. Um, and actually there wasn't anything before or after that minute. You can't really see it here because my kind of process of putting all these things together has created some blanks. Um, we'll go and look at the next one and see what that tells us. So that's rather similar, downward sweep. The clicks are structured, you know, they've got a the loudest cycle is number 1 or 2. Again, this very smooth clicks per second sweep. So it's a very similar one to the last one. And what's basically, you know, we struggled at the beginning, like, are these a physical process? Is it like bubbles coming out of the seabed or released from a sort of focal point for oxygen bubblification, if that's the word, on the surface of a seaweed or something? Um, um, But now I'm absolutely sure these are biological. There's lots of species of whatever they are that does this. Let's have a look at another one. Um, Similar looking thing. You've got this down sweep. You've got kind of coherent click trains. There it is in there. These are all rather similar. I'm sure I've got some that are a bit different. Okay, here there's something like very long going on. Um, um, and what you can see here is this amplitude profile is very flat through there. That would be extraordinarily unusual for a cetacean because it's narrow beam. If it just wanders around a bit, it will kind of show jumps in amplitude. Um, and this very smooth kind of click rate profile. Okay. Um, so here we've got some things classified as dolphin click trains, but they're very fast. This is going at 1200 clicks a second up here. So I'm going to zoom in on this one here. And just bring that down. So this is quite extraordinary. And this is thanks to Christy Macmillan and Barbara Merchant in British Columbia, where they are the kind of world capital for WUTs. And this is an absolutely staggering weak unknown train source. You can see this incredible structuring here of all these sort of successive peaks and this long decline. At the beginning, you get some louder clicks, a bit of a change in pitch. You can see some sort of slightly lower, slightly higher frequencies. And there's some frequency modulation going along with the click rate. You don't see that to the same extent with cetaceans. And then this click train kind of slows down and typically kind of fizzles out towards the end. So that is an absolutely staggering weak unknown train source. And here's another one equally awesome and from the same stable, as it were. So this one, the the FP3 has managed to track this profile. You never see anything remotely like that from a cetacean. And again, it's got this fairly level profile. I don't know what that louder stuff is there. It looks like another what's going on at the same time in the background. Okay, so they're terrifying, but in most places they're rare. I'm trying to reassure you now before you say I'm never going to use a pod again. And you know, honestly, I will certainly give £1,000 to anybody who produces a picture of a what's looking straight into the camera. Okay, show next screen. So here's a tiny little click train. I mean, tiny in terms of duration. It only got picked out by the classifier because things are so quiet around it. But actually, and surprisingly, it did get classified as a dolphin. But that will be because what's earlier in the same minute got classified as a dolphin, so the classified this feedback thing kind of lowered its guard. Here, looking down at the bottom here, you can see the red grass at the bottom. That's sediment transport noise, and then there's this what's here, which has got this starting off at like 1700 clicks a second, and this down sweep got the sort of frequency drift. It's got this louder start and it fizzles out, and the overall profile is, you know, relatively flat. You know, mostly with cetaceans it's kind of rising from a low start and doing whatever it does. Okay, so this is like a shorter click train, but again, typical of a what's. It's got the sort of big frequency changes through it, and it won't be part of an encounter. Yeah, so just looking at a number of these. So this one, that amplitude, that's really not like the tail beat because it's much too fast, and you've got this click rate modulation. Okay, so here's a tiny little click train. Isolated small brief click trains are generally rejected by the classifier, and you know, have to be rejected really. That's some noise trains that have got in there because there's porpoise identification. So okay, I think I've probably done enough here. I'll just look at the notes. What's multipath is rare. Yeah, it's just worth saying that. Okay, so just to, how long have we been going for? An hour. Okay, I hope you can take a bit more. I'll just close down that one, and we'll just look at what you do, the sort of routine when you look at a file. So this is the data that's on the website, and we've actually used it in previous tutorials from Babatonga Bay again. So what I always do is start off looking at all the Q classes. You can put that in as well. And all the species groups. And the reason for doing this is to see how they're grouped together and get a picture of the whole file. So down at the bottom here, we've got the pod is kind of not in the water, it's hanging downwards. Then it's in the water, temperature stay. Then it's out of the water again, and it's hanging downwards. And fortunately, all the detections, but you can get false detections when it's out of the water. You can even hear the boat sonar when it's just sitting in the boat out of the water sometimes. Anyway, what we see here with the species class is that the unclassified are grouped very tightly with the species. There's a place where they're not grouped together, and you might want to zoom in on that to see what's going on there. And similarly, the low quality trains are grouped with the high quality trains. Those are kind of good signs. You kind of should look at the warnings. So I've actually done this already. Warnings are only available from CP3 and FP3 files. So file 2, which is an FP3, it's actually got only one warning. Pod is more than 300 degrees from the vertical in more than 5% of minutes. That's actually when it wasn't in the water. These warnings are very cautious, actually. It's unusual to get a file with so little. We'll look at them on something else as well. And then the analysis page will do that. This is file 1, the raw data. Not generally hugely interesting, but looking at the FP3 generally is. So we saw unclassified was a fairly small fraction of those. So was low quality. We've got all the species in here, so I'll just take out like porpoises. We're actually the Franciscana here, Pontoporia, and the kilohertz is right, the click cycles is right, and the clicks per second is kind of fizzling out down here around 700. That kind of looks okay. So nothing very alarming there. Bandwidth, we're looking at dolphins now. The bandwidth, it's a funny measure, this, but basically it's higher in dolphins than it is in porpoises or NBHF, narrowband high frequency species. The clicks per second's got a lower peak generally for dolphins. Okay, so that's all right. And I think what we can do, look at the warnings, look at analysis. We will then actually look at a really scary file. Want to show from start. So this is the file from which those amazing WUTs came from British Columbia. And at this stage, you kind of see immediately that there's something strange going on here. The angle's all okay, the pod's sitting upwards, the temperature's kind of reasonable. The sound profile changes here, which, you know, could be weather or something, and the number of clicks, the black line is building up. But it's when we look at the second one, the species class, that's kind of looking reasonable here. But then here we start to get more and more with where the species is unclassified. And similarly, we get more and more where the quality is low. but the dramatic one is the very high proportion of unclassified species. And the top graph is quite extraordinary. This is clicks per second. And this color, aubergine, is supposed to be, is like very fast. And it's a very high proportion of very fast trains. Normally, you're seeing, clusters, which are kind of encounters with some of them having more fast trains than others. But here you've got this sort of massive exposure to, and if we kind of zoom in, we will get into a kind of a gathering of watts. Yeah, so there's one here that's like very fast. But anyway, we've kind of looked at those guys. Yeah, there it is. Some amazing kind of grouped down sweeps. Okay. So what else do I have to cover? Look at the warnings, look at the analysis. Validation. Okay. So I should have kept the Babatonga file open, but say you've had that general look at the file. Now you're going to do a formal validation of the a species of interest. So say that's going to be porpoises, high and moderate quality, high species confidence. The data you will kind of use, and you want to know what your error rate here is. So you go to the filters and files page. Okay, you've got to tell this. It's going to ask you what file you want to validate. So select this file for action. That's just like the top panel there, which was file 4, which was an FP3. Okay. I'm going to look for 100 at 100 minutes with detection. So set validation sampling points. 100 sampling points are now set. Use Control and S to move from one to another. Okay, Control and S. This is the first minute. Okay, lovely frequency. So these you do with these what we did earlier. And I'm just going to bomb through just to give you an idea of kind of quite how far. So I would say good, 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 etc. And you do that for your dolphins separately. You set separate validation points, and you count the number of minutes that do not have a single true train. So if you're looking at detection positive minutes, you've only got to have one true train for that minute to be positive. Okay, so you have actually got in the pack, you've got this document on validation of FPOD data. So we've kind of looked at all this, but this document is quite hard to read from the start. And that actually it's part of work done with Julia Vanchikova, who's part of the Black Sea Trends project, and she's doing a paper on validation. She's looked at 168,000 click trains, and it will be a very interesting paper when it comes out, and it's got a better description of the FPOD than has been published elsewhere. So this one shows you multipath replicates that we've talked about, and for a porpoise, all the multipath replicates, or nearly all of them, should be in the frequency range of porpoise clicks. Here's a dolphin click train. So it's actually at porpoise frequencies, but the multipath, which is nice, regular multipaths, absolutely belongs with the click, is lower frequency. So the high frequency is coming straight out the middle of the beam, but out of the side of the beam, you've got some lower frequency, which is get bent around and brought back into the pod. This is a spurious click train. We looked at something like that. This one is about the interclick interval, which is showing you the things we looked at there. This is contrasting this nice amplitude profile you get with the tail beat rate against a noise train. Okay, so I didn't say much about distinguishing species, which in the Black Sea data is like very relevant. And here you've actually got porpoises, nice classic porpoises, and nice classic dolphins, and probably the two overlapping here. So the approach here basically is you just validate them. Does the if you just had that little bit of dolphin, you'd look forwards and backwards. You'd look for these fragments of click trains ahead and later to make it part of an encounter. And here we've got a dolphin cropping up actually in the middle of some porpoises, and you can see how these features are kind of helping sort them out. This dolphin's got frequencies that are bang in the porpoise frequency range, and they can be long clicks. Here, their narrowband high frequency index is really low. You've got multipath at lower frequencies, and the classifier got it right. Okay, here's a point I didn't really bring out, I don't think. With WUTs, you often see the beginning and the end of a train. You don't really see that with dolphins and porpoises because they're producing a really long train and you just get a fragment as their beam sweeps across the hydrophone. But this WUTs, whatever it is more or less stationary. It may actually be sitting on the hydrophone. It may be a little copepod or something. And so you see the train sort of start. So it's kind of there's sort of slow clicking, then it goes into a fast click phase, and then it fizzles out. They typically fizzle out. They often don't have this. But the correlation between amplitude changes that build up and rate changes is very typical of like a static source where you're seeing the start and end of a train. I hope I've explained that well, because it's actually a difficult thing. It's taken me quite a long time to get my eye in for, okay, that train is actually starting there or ending there. Here's a WUTS that shows a halving in click rate. You can sort of see that. And it's got this sort of fizzling out characteristic. This is portraying an encounter which we looked at, with nothing much going on. So if you get an isolated train, the classifier says it is a porpoise, and you think, well, not really going to buy a single train. But if you scroll backwards and forwards, and you can see train fragments, and you have to zoom in to sort of get a good feel for them beforehand and maybe afterwards, then and especially if you've got some multipath, you can say, yeah, it is a single train, but I'm sure it's a porpoise. Right. I think that's everything I've got for you. So yeah. Okay. So are there questions that we need to deal with? Dan, can you give me some guidance here?
Well, we haven't got any questions in the chat. I think you've covered pretty much all the things I do. I mean, I suppose one thing I do differently when you were going through the like the dolphin, but actually no, the 100 samples.
Yeah.
I probably have more parameters open. I think you had 4 open there, but I know some of them tell you multiple things, which obviously I didn't used to. So I forget which one it
Yeah.
was now, but there's one that shows cycles, another one that shows amplitude, but at the same time it's showing you species class or Q class. Forget which way around it was now.
Yeah, that's a good point, actually. And I actually do the same. I have more open, and I'd encourage people to kind of very mess around very freely with what parameters you're showing. So if you're working in the Baltic and your focus is on porpoises, you'd want narrowband high frequency index as one of those. But if you're working somewhere which has got no NBHF species, you're looking at dolphins, you might not want that. So basically change those things very readily, and you gradually get familiar with using them. Yeah. Okay. I mean, what?
Sorry, I was
Sorry.
just going to say there's a couple of questions in the chat about validation. I can read those out to you, or you can.
Oh yeah. Okay. Okay. Oh, so the bad validation from Marco. Yeah, that's a good question. Yeah, and that one and the next question, really. The key thing is how big a difference are you looking for? If you're saying, how does this site differ from this site? You're likely to get differences in the number of animals of, say, 500%. And you could tolerate an error rate of, say, 20%. But if you're looking for a trend over time, you don't want you want tiny error rates, so you'd validate like a lot more than 100, and you'd be unhappy if you had more than, say, 2% positive. So you have to judge it against the size of difference. What error rate you're finding, is that bigger than the differences in the statistical test you're ultimately going to use? So actually it's a harder question than it looks. And if you ask a statistician, they will give you kind of chapter and verse on this. But you might find a file that was essentially unusable. It's very rare, actually. And that data from British Columbia is the hardest I've ever seen. I mean, it is actually usable with some very tough filtering. So Luana says, what should we do when we find a false positive? You shouldn't do anything except write down on your bit of paper as you go through, like how many false positives you found. It's tempting to kind of edit them out, and the software lets you do that. But really, you really don't want to do that, because then you can't compare that data with other data in the future unless it's edited by the same person, or if it hasn't been edited. So basically you keep a record of the false positives, and you make this decision about whether the number's unacceptable rather than doing anything to them.
I suppose the only exception to that would be if you had a file that had a low number of detections and an even lower number of true positives within those, and if that was consistent, you could mark the true positives and export
Yes.
data based on that. But then you do kind of run the risk that if in the future those proportions change a lot, or you then have the situation where you have a lot of detections, and you've kind of committed yourself to looking at every single detection and validating it, then yeah, it's
Yeah,
difficult.
no, that's a good point, Dan. And the team in Mexico who've looked at the vaquita, you know, and the vaquita's down to like 10 animals or something. They check every train. They do remove every false positive. They don't have to look at many clip trains though, because there are so few. I sort of would slightly differ from what you said, Dan, though. If you had done that where there were very few animals, if you then have another site with a lot of animals, you don't have to worry there because the fraction of false positives is then very low. So in the Samba data, we did look at the sites which had less than 50 detection positive minutes, because they were where we could see the false positives. Mostly we couldn't find any false positives, but we could see them in those places. And that removed a few sites from the map of where the Baltic harbour porpoises were. So there are some cases, as you say, Dan, where there is a case for editing them out. And you can either remove their species class or you can mark them and then filter by marked or unmarked.
I generally do that because then at least you've got the option of going back and seeing what was there. Whereas once you've removed them or reclassified them, the data's changed permanently then, isn't it?
Yeah, marking is nice. You have to remember you've marked that far. So yeah, Chris is asking, can you mark a false positive? Yeah, you put your pointer in high resolution to the left of the click train, immediately to the left. You right click and the pop-up menu
Do
has
you want to just demonstrate that, Nick?
yeah, okay, so let's fire up FPOD, open files, Babitonga, okay, 10 milliseconds, show from start, show next screen. Okay, so here's a I'm just going to get rid of this color by train number. So here's a sonar. Say it had identified that sonar as a porpoise. I can go here, I can click and mark this train. It's now dotted lines. I can now go over to the left. Train fills, mark trains excluded, refresh. Now, magic, it's disappeared. Also, I can then, you know, go to analysis and analyze, like, that was a sonar. Whoops. I can analyze with that one excluded 3,254. I can do mark trains only. That one had 366 clicks and I can see all its characteristics. Or I can include it and it's now added into the total. So as Dan says, if you mark them, you've sort of got access to them still, and you can look at the characteristics of the ones you pulled out. And yeah, okay. There's another concept here that's just worth mentioning. You want to exclude trains that you're not very confident are, say, porpoises. But then if you're not very confident, you say, well, what do you think they were? And the answer is, well, I think it was a porpoise. Well, but I wasn't very confident. So you end up in this situation where nearly all your false positives, your false positive porpoises, were actually porpoises. That is I think that's a very good paradox on which to end the session, unless we've got other questions. Well, just to say, if you think of other things, do send us an email, and if you don't get an answer, send it again.
Well, actually, Nick, just one thing. I thought of when you were going through samples earlier, which was depending how it's scaled. And I know we covered this in previous sessions, but if anyone missed those, especially the amplitude, it will quite often sort of max out, so you don't see the amplitude profile. So you can just downscale that by hovering over that that parameter data that's displayed and hitting F6. Just sometimes makes it a bit easier to see quickly if the amplitude profile looks right.
Yeah, that is very useful. I was doing it quite a lot there, but it does help a lot. Yeah. Okay, so
There's another question from Chris. Nick, sorry.
oh yeah, the high species confidence tick box. This one over here. It's kind of knocking out about 2% of dolphins and maybe 1% of porpoises that are a bit close to the line as to whether that really is or isn't a dolphin or a porpoise. So if you've got a reasonable number of animals, it's not going to make any difference really to your statistics. It would just be in that effective detection radius would contract slightly. But the value of it is if you hit really bad conditions and you may have a long running project and you suddenly get somebody anchors a boat with a sonar near your logger and is going to inject more false positives in, this is kind of helpful. And so I would say just keep it set. But if you were, say, looking for the last 10 vaquita, you'd actually untick that and you'd validate the low quality as well as the high and moderate, because there you're not really, you're using the automated process to guide you, and your final classifier is a human. That last question, when can you use the FPOD app to look at CPOD files? Yeah, what Luana, what you said there is correct. You should process CPOD files in the CPOD app and then do everything else in the FPOD app because it's more powerful and flexible. Yeah. Okay, well, thanks guys. Thanks for surviving as ever. And yeah, send us any questions and we'll put the video recording online. So I think Sibylla, you can take control of that now.
Yes, and the recording will be sent out either later today or tomorrow, so look out for that. And I'll stop it now.